So, good evening, everyone, or morning, afternoon, wherever you're joining from. It's evening over here. So, anyways, I'm super excited to have you all here today. This is our second MLflow webinar. So our first part covered experiment tracking, and that's what I will go through very, very briefly today. If you were not there last week when we discussed that, do not worry at all. Today's session is nearly disjoint from the experiment tracking part of things. Both are very awesome and work in tandem in effect. However, it does not require the interoperability of knowledge between both in order to use one component. So that is something that we will basically leverage today. So to quickly recap what MLflow tracking is, right? Last week we discussed MLflow experiments, runs, as well as logging parameters, metrics, and artifacts. We were able to replace spreadsheets and Notion pages, basically any manual form of logging, and instead use MLflow to automatically track our experiments. This allowed us to not only ease the process of tracking the data where we don't have to input information manually, but also allowed us to compare experiments across or compare runs across different experiments, as well as log various parameters and compare them. So it's through various runs based on input parameters, as well as log artifacts, where we basically save our actual resultant model for use later on. Now, that later on is what we are going to look at today. The concepts of experiments and runs are very flexible. They can depend on your situation and preferences. But the main distinction between an experiment and a run is the fact that an experiment is considered a hypothesis. So if you want to evaluate, say, what hyperparameters work best, you would set that up as one experiment. And within that experiment, you would have many runs that explicitly specify how a single explicitly specify a certain set of hyperparameters. Then you would evaluate if you get the better loss on which one, and then pick that on the basis of whatever the result of those runs are. So that experiment basically becomes a sort of an umbrella term for a series of runs. However, it is also important to note that you can compare runs between two different completely disjoint experiments without any trouble at all. So that is also really cool. Each experiment, of course, can have one or more runs, and you can log any parameters, metrics, and artifacts that you want to keep track of and compare later on. So when used this way, MLflow is in effect a digital lab notebook. You will recall that from our last workshop that there are several scenarios that are available. But when you use DagsHub integration with MLflow, DagsHub does all of the MLOps heavy lifting for you. And this is basically what we set up on our end. You have your local host, which is your device or any device that is actually training the model. You have a remote host, which is what DagsHub provides, that contains a tracking server with an artifact proxy. It uses SQL Alchemy to store runs, metrics, parameters, and tags via PostgreSQL in our remote host itself. And we also set up an S3 bucket where you can set up your models, any images from your evaluation, or certain configs that are large in size as that are generated as a result of your training run. So the artifact proxy part of this is basically us not using the is the local host using a single HTTPS remote to deposit all of the data, with whether that is an artifact or it is an experiment tracking run. And we manage the authentication for the S3 bucket and deposit the actual artifacts that need to be deposited into the S3 using Porto. And this is all handled on the remote side, so you do not need to worry about it. And we provide this remote MLflow server with every single repository completely for free. So let's cover very quickly today's agenda. In this workshop, we are going to expand our MLflow knowledge and learn about specifically the model registry. We're going to be able to log and register models to this registry. The log and register are two different things. There is a subtle distinction, and we'll get into that later. They're not synonymous. Second, we will be able to load models from the registry. Third, we will deploy a model to Amazon SageMaker using this registry. Finally, we will create a Docker image that can be used to deploy a model anywhere. So this is a generalized one-size-fits-all solution for mostly any of your problems, because Docker is awesome. So let's get started. Right. First question, I guess, that I had when I started to learn deployment is, why is it so important to learn? Right. And the answer in the end is fairly obvious, actually. You can have the brilliant, most state-of-art model inside your SSD, but if it is never deployed, and like you have the state-of-art model that can, figure out the cure to cancer or something, if it's sitting in your SSD gathering dust, it basically has no value, even though it has the potential to be extremely valuable. So in order for a model to realize its potential, it needs to be deployed, and that is why it is incredibly important. We want to do it in a way that is not works once and then possibly never again. We want it to be able to be not just directly servable, but also scalable, in the sense that it should be able to handle a high throughput of users without buckling, which is how we would be able to deploy it in an effective manner. And MLflow eases a lot of that process for us, which is what is so fantastic about it. So model registry, right? To get started with that, it is a centralized store for your models. It provides you with a place to put your models related to experiments and runs, and includes stuff like model versioning as well as stage transitions. There's a superb graphic, I think it's a little bit in the bottom, but we'll get to that soon, that makes the distinction between all of these terms very, very clear. By keeping track of these things within the model registry, MLflow makes it very easy to determine which model you need to deploy to which environment. It makes the process less prone to error, and make sure that you deploy the correct model at the correct time and don't have an experimental thing that has not been tested running in production, right? So it's basically idiot proofing, and that is very, very, very important, especially when we do not have the time to perform due diligence, especially if that can be automated. All right. Finally, the important concepts that the MLflow model registry has that are relevant to note or know before we get started. The first one is that of a model. It is something that is created from an experiment or a run, and is logged using MLflow.framework. So that could be TensorFlow, it could be PyTorch, it could be FastAI, any of the frameworks that MLflow supports. And then the .log model is just what actually logs is the function that actually logs it. Registered model is a model that is registered using the model registry. It has a unique name. It contains versions, so version 1, version 2, version 3. It has transitional stages, so either it is in experimental stage, staging stage, production stage, or an archive stage. Model lineage, so basically the various stages of the model itself and other important metadata. Third is model version. Registered models have one or more versions. The initial version is 1. Version is auto-incremented when new models are registered using the same model layer. The fourth is a model stage. These are predefined as staging, production, and archive. Currently, custom stages are not supported, but there is an open feature request that aims to add this. I think this feature request is still open, but I can verify that as soon as the browser opens. Anyways, annotations and descriptions. You can use Markdown to annotate the top level model or any individual version with any information that you want that may or may not be useful. So this is like a README for the Markdown file, basically. I want to see if it's open. Yeah, it is still open. So custom names are still not there yet, but I am confident that they're getting there. So as I mentioned earlier, that there is a subtle difference between logging and registering a model. You can think of them in terms of their purpose. The logging of a model is important for the reproducibility aspect. Registering a model is important for the deployment or the production aspect. You can, however, do both logging and registering in a single step. Just as importantly, you can not only log and register your models to this registry, but you can also load and deploy them. So we are during the entire extent of the machine learning lifecycle that MLflow really loves to sort of brand itself against, right? We have this superb graphic that describes basically everything. For our first webinar, we covered the MLflow tracking server, where we discussed the parameters, metrics, artifacts, logging that plus metadata. So these are mostly stuff like, say, any pre-processing technique that you may have used, and models. So that's the actual thing that we're looking to get. So that is, I think, the most important one. So you have the tracking server, and from the tracking server, that model itself is bridged towards the model registry. You have a couple of stages. So from experimental through the archive stage, and you can see how the transition happens from a data scientist to a deployment engineer, wherein data scientists manage the experimental part of things, where they design interesting architectures, figure out what works best, fine-tune hyperparameters, and then set it to be useful in production. Then you have your deployment engineers that probably take over from the staging aspect, where they perform unit tests and give it that final approval to go to production. And once that is in production, that is mostly the domain of the deployment engineer. Then the deployment engineer manages the models, ensure that the deployment aspect of it is handled. That means it can take a lot of requests, it performs load tests, it doesn't go down like US East 1 did yesterday. And finally, the archive state, when you develop, or you as a data scientist develop a new state-of-the-art model and replace your old state-of-the-art model. So then that model or the stage for that model is updated to the archive stage, and you can set up your deployment solution to automatically pick up the model that is present inside the production stage. So that way you are able to ensure that you always have the latest version running without having to manually update it every time your data scientist develops a new interesting model. So finally, once you are able to go through the happy pipeline of tracking a model, registering the model, and deploying the model, you can also change some specific aspects of these registered models. As an example, you can change the model name, the model stage, as well as the model tags and attributes. And as you would have guessed, out of all of these, the number 2, that is updating the model stage, is possibly the most important, because that is how you indicate a model has moved from a staging stage to a production stage, and it keeps your entire organization on the same page with regards to what the status of a given set of models are. This is something that is also important within the happy part, which is why it makes it super important for us to cover updating the stage itself. But that said, it's also very, very easy to do this. It's as easy as just updating it on the UI, just switching the button. And if you want to do that programmatically, that's also very straightforward. We will cover both of those today. Searching. The longer a project runs, the more experiments, runs, and registered models you will have. Keeping track of all of these models would be a nightmare without the ability to search. So MLflow addresses this by default, wherein it includes APIs to fetch all of your registered models, as well as search for models by either exact or partial matches using an SQL-like query format. So it makes all of that also very, very easy. Finally, we have model serving and deployment. It offers options for both serving and deployment, like logging and registering models. There is a difference. It is just that the difference is subtle. But again, it is an important difference. Model serving uses the current machine that you're using, whereas model deployment can be to any machine. The model deployment is also dependent on creating a Docker image. So in every case, model deployment creates a Docker image that encapsulates whatever deployment or whatever model you are looking to deploy. So model serving, to start off with, you can serve your registered models locally using the CLI command MLflow serve. By default, this sets up a REST API which serves the model on port 5000, And the endpoint for this is the invocations. So you would basically go to your local host and the port 5000, you would get your MLflow UI. And within the invocations endpoint, you would be able to access and request anything from your, or like request predictions from your registered model, and it gives you the relevant output. Behind the hood, MLflow uses Flask in order to create the web application. When you're ready to deploy a model, there are a couple of built-in options that you have. Firstly, MLflow has built-in support to deploy to Amazon SageMaker as well as Microsoft Azure. If those two don't work for you, there are also third-party plugins that are available that allow you to deploy to Redis AI, ThoughtServe, Algorithmia, as well as Razor. If none of these services are your personal or professional preference, so if you like GCP, you can do a couple of things. First, you can set up your own custom deployment plugin following the examples above, or you could use MLflow to generate a Docker image that wraps your model in a REST API and just deploy that using any container management service that exists within your cloud platform of choice. Out of these two, I definitely prefer number two simply because it is very straightforward to do and doesn't come with the burden of developing something or maintaining something additional on the side in case things break or APIs update, which is very, very popular with any framework. Even Torch updated very recently, as did TensorFlow. So it's very important to have that in mind as well. By creating a Docker image, it gives you the ultimate flexibility to take your model anywhere, simply because container management services exist for basically every single cloud platform today. By default, this Docker image uses Nginx for tunneling and Unicorn for the WSGI for process management. There is this nice meme that I think summarizes Docker perfectly, where there is one developer that goes, it works on my machine, and the other developer says, we will just ship your machine, and that's how Docker was born. It basically creates a container, and that container is almost like a virtual machine, except that it shares the host kernel, so it is also super efficient and just creates a separate file system. But I digress. If you are unfamiliar with Docker, you can check out this beginner-friendly tutorial. It's very cool. The documentation is also fantastic. So I definitely recommend checking that out. But for the time being, just know that it's a way to build, test, and reproducibly deploy applications using containers on a variety of hardware and software. Additionally, it's also very, very secure, simply because vulnerable applications cannot escape outside a given container. So it ensures that if one service that you deploy is impacted, the other services are still all right. So that is, I guess, the more or less of the theory aspect that we have. So let's recap our sample project that we covered from last time. So if you recall, we were working with a small model that can classify whether a video game contains Mario or his arch rival Wario. So there's Mario over there to his left and Wario on the right. In our case, we are 8-bit fans, so we have a video game screenshot. This is Mario over here, and this is Wario over here. Now, I guess our objective would be to set up the registry aspect of the project using using the sample-based project that we would fork on or fork off of. So that, I think, concludes our theory aspect. We have all of the practical deployment from this point on. If you have any questions at this point, I would love to take them. And maybe I'll drink a sip of water and we can start again in a minute or so. Okay, I have the chat up and I do not see any questions. So I guess I will move to the fun practical part. So to get started, please fork the base repository to your own personal account. that will allow you to set up all of the or like run all of the things that we do in your own repository. So I will do that very quickly. Just click the full button. You can change the name if you like. I will keep it the same, and that should set up the fork. So this is the fork of the repository that got I started. I will run the DagsHub or like install the DagsHub client, because that is something that we will need for authentication, um, as well as dataset streaming. You can enter the credentials for your DagsHub account. So your username, mine is Jinen, this is my email, and the DagsHub repository. If you change the name, you change it, but if you haven't, just let it stay the same. So once DagsHub installs, we can, and this is run, we can also create an OAuth token that allows us to effectively log in to DagsHub. So we don't have to enter any authentication details further down the line. And our actual token itself is stored via the OAuth token inside this variable. So to get started, I will clone the project. So set up or configure Git with all of the details that we had up above, and clone the actual repository that we just set up. Once that's done, it CDs into the DagsHub repository, and we should have that ready. Now, the next step, obviously, since this is an MLflow workshop, we will have to use MLflow itself. It is installed like the DagsHub client using pip. There are a couple of installation candidates that you can use. The first one is MLflow. The second is the extras library that contains a bunch of third-party tools that may or may not be relevant, but are a bit bloated. Finally, there's MLflow Skinny, which is a lightweight version of MLflow. If you are deploying it on a edge device or something, that would be the preferred installation candidate. So those are the three for today. We'll just be using the default MLflow installation. So I will just run that. Next, we set up the environment variables that we need. The first one is the MLflow tracking URI. This is recommended to be defined within the code and not as an environment variable, because your remote URL changes from different projects. So if you have two different repositories, you do not want one experiment to be tracked to the wrong repository. So this is not recommended. However, since we're working on a collab environment for this individual project, it's okay. But yeah, that is that. We are also defining tracking username and tracking password. This is good to define as an environment variable, because this does not change between two different projects. That is that. And in order to actually import or use an MLflow library, all you really need to do is import MLflow. So to start with the initial training, let us run the following training script. And let us check out or go through the training script very, very quickly to see exactly what is going on under the hood. So here is our training.py script. And we can see that we have the MLflow.set tracking URI, where we get the MLflow tracking URI environment variable and set it within our code itself. And this basically lets it know to use the remote MLflow server and not initialize an MLflow server locally. We have a get dataset function that gets our dataset, our training, validation, and test datasets that we use for training. We have our model that is a sequential model. We have a convolutional, three convolutional blocks with a convolutional and max pooling layers, and we flatten that out. We have two fully connected dense layers with a dropout in the middle, and this leads to the final activation, which is sigmoid, because it's a binary classification task. If it's above 0.5, we determine it as containing Mario, and if not, it if the confidence is below 0.5, it is considered as containing Wario. We combine this with the item optimizer. We have, I can scroll there to just confirm that our learning rate is defined within the function definition. Here is we're using binary cross entropy as well as accuracy for metrics. This is our actual training code. We get the experiment ID using the helper function that we have defined. I can open that real quickly as well. And this is the helper function that we defined. we have set the experiment name as Mario_Wario, and this sets up the training run. Once we do that, we log a couple of parameters, a couple of metrics, the artifacts as the model directory, as well as a random text that we think may be relevant to the run info.txt file. This is all stuff that we covered during experiment tracking. So if you're curious about this, we should have the YouTube recording for the workshop that we conducted last week up. So do check that out, please. As far as the accuracy for our model is concerned, we got a validation accuracy of 60%, which is better than a coin flip. So I will take that. And our test accuracy is also marginally better than a coin flip. I will still take that. But yeah, that is our model itself. It's not the best, but it will serve our purpose as far as understanding the entire pipeline goes. So we will run a script that gets the last run ID named Mario_Wario and stores it into a environment variable. This will be important later on. And we define run_ID over here. I will open up the script really quickly. It basically just takes the first argument that we set up, and the first system argument, set that as the actual run ID, and we have hard-coded Mario_Wario. So I will do just that, and it gives it saves the ID to the environment variable run_ID. Now, if we run MLflow runs list experiment ID _0, we will be able to also get the actual experiment ID, and within that we can see this run ID, which is exactly the same as the one that is there over here. So that's just us doing a sanity check on the information that we have. Logging models. There are a couple of programmatic methods that we can use in order to log models. The first one is MLflow.register model. And we use this after the run has completed and you want to register a model after the fact. So an important consideration to note is when you trigger a register model function, oops, network error.
Yeah, we lost you for a split sec. Just for the last 20 seconds. Probably you had a disconnection in your internet, so maybe you need to rerun it.
Yeah. Sure. So what was the last time?
No, I think you probably need to rerun the notebook. Was it disconnected?
Yeah, it was disconnected, but the environment is fine. I can just confirm that very quickly. If I get the correct output, they should be fine. Otherwise, I'll rerun it. Yeah, we're good.
Okay, so just start from like logging models, I think.
Okay, awesome. Thank you, Neil. So logging models, there are a couple of programmatic methods that we can use in order to log models. The first one is the register model API. We use this after runs have already completed and you would like to register model after the fact. So an important distinction to note is within our train.py code, we can see that we log artifacts, but we do not register the model itself. So in this case, in the distinction between these two functions is that when we log artifacts, MLflow does not consider the actual code that is present within the data that you store. It simply stores the data as is. And within the register model, you are setting it up within the model registry. In this case, the model actually is has to be run and loaded by MLflow itself, in which case they are a lot more strict about all of the different variables that you have within your model. So if you're implementing a custom loss function, for example, you might have to set that up separately within MLflow in order to run it. But if you log an artifact with a custom loss function, that will probably not give you an error simply because it doesn't have to run that code at all. It is just storing the data exactly as you give it. So that's the register model function. We set up our run ID from the environment variable. We set up the subpath name for the run itself. and we select a name for the model to be registered. So I picked Cool Mario Model, and from there we can build the run URI. This run URI is basically the internal path that MLflow uses in order to specify the type of object. So in this case, this is a run. You could substitute this for models and query the model registry. And under that, we basically specify the path, which is the run ID, as well as the specific subpath itself. From there, we can register the model and let us see this run in action. Very quickly, it says that it has successfully registered the Cool Mario model. It set it up into the model registry and created version 1 of this model. So by default, if you don't specify version, it auto increments it, and if it's a new model, it will set it up with version 1. Finally, we can also register models using the MLflow.framework, so whichever framework of your choice, and then .log_model function. This basically logs as well as registers the model in a simultaneous fashion. It is best done from the train.py script directly after training. So that would basically come in right here. In train.py, you will find the line of code on line 144 right here, and replace it with the log model function, where you specify your model equals the model object itself, the artifacts path, which is the model directory, and the registered model name, which in this case is Ultimate Mario Model. So I'm going to very quickly copy and paste this line into the actual Python file. I guess I can copy it from here. That makes it easier. Okay, and I will replace the log artifacts line with this. Let me close this and make this a bit bigger so it's easier to follow along. But we have, MLflow.tensorflow.log model. We specify this, the artifacts path, as well as the registered model name. I'm going to save this and head back up and run this same script again. And this thing again. Give me a second. I need to disable the install hooks for running device. And now it will retrain the model with, and once this training procedure is completed, it will automatically log as well as register the model. So let's let this run very, very quickly, and hopefully the accuracy is a bit higher at this point. (62%). Lady luck has rained upon us. Okay, cool. So we began saving the model. This MLflow started setting this up, and MLflow encountered an unexpected error while inferring pip requirements. It's a warning and not an error. We are cool with that. It created the version 1 of Ultimate Mario model, which is fantastic. And yeah, that sounds good. Let's fetch all of the registered models from our remote client to see if all of these have been logged. So we see Cool Mario model right here, the Ultimate Mario model right here. This contains the original run ID, the 9cc one that we had and defined way up in the beginning. And the Ultimate Mario model has a custom run ID simply because it is set up with a new run within the Mario_Wario experiment, and that has its own custom ID. So from here, we can also query some specific models. So if we like, we could, over here, what we did was we set up this filter string with the SQL-like query, where we said name, like, and then anything. So it basically returned us all of the models. We looped through all of the models with the latest version of the model and printed out all of the information that we had. So if we want to say restrict our search to only the ultimate series of models, we can just specify ultimate %, and then it will restrict that search to that. So if I run this script that has nothing different from the thing up here, but besides the actual filter string, it shows us that we only get the ultimate Mario model and not the cool Mario model, which unfortunately, yeah, it just doesn't sit within the string specification. So that is, I guess, the registering part covered. Now we can talk about updating the actual model information itself. Updating the model is incredibly important. Besides updating the name or the tags, the important one, as we previously covered, was the model stage itself. So renaming the model, let's start with the easy one, I guess. We can rename ultimate, oops, because I set this up as, I changed the name, but if I think this exists for your repos for your notebooks as well, I don't think it will change very much. But yeah, feel free to update the name from cool to ultimate. And we want to rename this ultimate Mario model to great Mario model because we realize it's not as awesome as we initially anticipated. So I will do that, and very quickly it just renames the model exactly as we expected. Finally, we can also update the stage. This script is again very similar. We define a client and we use this transition model version stage function. We set up the name of the model, the version that we would want to update the stage for, as well as the actual stage itself. So we want to set the stage from none to staging. We could do this using the Python API if I would run this cell, but I would like to use this moment to showcase using the MLflow UI to make this exact same change. So I will open this in a new tab, and this should set up our MLflow. Um, oh, come on.
It works, we see it.
Am I back?
Yeah.
I apologize. Okay, what was the last point in which I was disconnected?
You weren't really disconnected. It took you a while just to load the MLflow.
Oh, okay, awesome. I thought I was disconnected for a second because it said my connection was unstable. But okay, here we go. We have the actual MLflow UI itself. And if we go to the models tab, we can see our cool Mario model as well as our great Mario model. And this is the one that we renamed. So if I go into this model itself, I can enter the version 1 and update the stage from none to staging. And we have this option to transition existing staging model versions to archived if you do not want multiple versions on the same stage. This is probably the most relevant for something like production, unless you're A/B testing. But since we only have one model version that is currently logged, it doesn't really matter if you set it. So that is completely your call. Now, if we verify, and just to verify that we can see the changes that we made from up there here as well, we can run the exact same code where we get all of our models, and we can see that the stage is updated to staging for the great Mario model. If we scroll a little bit up, we can see that the stage was previously none. For the ultimate, I guess I didn't query the great yet, but okay. This it basically updated the stage, and that's the updating the stage part of it covered. In order to load a model from the MLflow registry, so let's say you have completed this entire process and you're performing the handover to your to the DevOps engineer. They do not want to set up the entire training sequence just to be able to load the model. It kind of defeats the purpose of the lifecycle management utility. So here's how we can set up loading a model directly from the registry itself. In order to load a model, you first need to construct the model URI, which is similar to the runs URI. It's not similar to the runs URI, but it basically changes the runs term to models, and then you specify various versions from there on. So for the models URI, you have this following format. You specify models, then the model name. So it could be Great Mario Model or Cool Mario Model, because those are the tools that we have right at the moment. And both of those only have one version, so we would specify the version 1. Alternatively, if we want it to dynamically update, we can also set up the model stage, so we can only pick out the production model at every point in time. So whenever the model is reloaded, it automatically picks up the last updated version directly for you to use. So that is our model itself. Here is how we can actually load the model into TensorFlow. So we specify the name, Great Mario Model, the version, we get the latest version, we specify the name and get the first, it returns it as a list, so we get the first one and the last version, we construct the URI itself, and then finally we load the actual model. We use the MLflow.TensorFlow, so this is replaced by any framework of choice with the load model and specify the model URI, and it gives us this model object in our backend. Once we have this model loaded, we can test it to make sure it works. I define this very straightforward load test image function. We specify a image path, load it into Keras, convert it into a NumPy array, normalize the pixel values, expand the dimensions to include a batch size of 1, and get this image. Then we run inference on this image. Very quickly doing that. So this is a Mario image, and it has the prediction that we got from here is 0.48. So it actually is classifying this as Wario's. This is an incorrect prediction, unfortunately. But that's basically us running the prediction from the model that was not present in our environment, but from the remote MLflow server, which is pretty awesome. So what if you do not use Keras? There are many other supported frameworks, but what if you have a special case where you have something proprietary and that is not currently supported? In order to support, MLflow allows or provides you the opportunity to develop a custom class built on the base classes that they provide that allow you to set up the model registry even on a framework that it has no idea about. So it is completely generified, right? The steps for that are fairly straightforward. You would create a wrapper class that inherits from MLflow.pyfunc.python model. You would create a predict method that takes two things, the context as well as the model input. And optionally, you would write a load context method in order to set up your model. So it's basically as follows. We have the Mario model wrapper or class that we have just defined. We are extending it from the Python model class that we get from MLflow.pyfunc. Since we have a Keras model, what we're doing is basically recreating their Keras functionality, but it would apply interoperably to any MLflow, to any Pythonic function, provided you are able to perform the inference using a Python script of your choice. So from TensorFlow, we import Keras, we use this load context function to set up the model object where we load the model from the artifacts. Then we set up the prediction function where we have the context as well as the model input. We set up the model input to bytes. We specify this pre-processing pipeline, basically load the image from our model input, set that up with the same pre-processing setup that we had for our previous case. And then finally, we get our resultant inference. We return this as a dictionary, and that can be converted to JSON if you are using curl requests in order to perform model inferencing. Additionally, you would also need a conda_environment dictionary so that MLflow knows what libraries are needed in order to run the model. In our case, we need MLflow. Obviously, we need Pillow in order to load the images. We need Cloud Pickle to load the actual model from the remote registry. And we need TensorFlow in order to load the actual model itself. And we specify the versions that we have from our current environment. So we set that up within this conda environment dictionary. The rest are basically defaults. Name is Mario underscore environment. You could you could specify that as anything provided that it is consistent. For Python version, we also specify the version that we are currently using so that it doesn't cause any issues if it is using a different model version or a different Python version. So I will copy this entire class that we had defined to the Mario underscore vario source and register underscore pyfunc class. So we have this boilerplate set up. I add this class object or this class itself that we are going to use as our actual inference or our actual inference endpoint. This will run whenever we query images to it. Then the auxiliary variables that we need, so the Python version as well as the conda environment. Now, once these are set up, you would also have to set up an artifacts. Okay, wait, let me fix the indentation very quickly. You will also have to set up the artifacts directory, which will be part of the context that your wrapper class receives. So if you noticed over here, we used the context variable, and within that we use the artifacts path. So that's exactly what we are looking to set up over here. So we basically set up the artifacts dictionary and give it a path key with the models directory that we have specified up top right here. So these are our priors sorted out. Now all we need to do is actually define or initialize the classes that we have set up. So first we instantiate the model wrapper, we set up the experiment ID, and start the actual run where we log our model itself. So I will do this instead of the TensorFlow instead of the TensorFlow module. You can notice that we use the pyfunc module because we are specifying our own Python function. We have the model and the experiment IDs that we are setting up as input over here. So we have the Python model that we set up, the conda environment. This is something that we defined earlier. The artifacts that is present within the context itself, and the registered model name. We are specifying this as wicked Mario model. Again, this can be anything provided that it is consistent. Once this is set up, let us quickly run this code. And once we get confirmation, we can also run it to make sure that our wicked Mario model has been successfully registered. And this is running our changes from end to end, which is super, super awesome. So successfully created wicked Mario model, and it created v1 of this model itself that it logged to the registry. Just to make sure that it works one more time, we can run all of or identify all of the models that we have, and we can see that it has logged wicked Mario model with its own run ID that was set up right here. Again, it has version 1 and no stage by default that I can show as soon as I can clear these out. So right there. Once that is set up, we can save all of our changes. So commit and save all of our changes to ensure reproducibility. I have set it up as added. I have set up the commit message added model registry. Again, this could be anything. And once that's done, you could push that to your Git remote. That covers the entire deployment aspect from or the actual serving aspect. If you want to talk about the deployment aspect, we will basically talk about doing this through AWS or Amazon SageMaker. To start with, you would have to create an AWS account. You would need a credit card for this step. You would have to set up IAM as well, so identity and access management roles. And install the AWS CLI in your environment using pip. So pip install AWS CLI, similar to how we install MLflow as well as the DagsHub client. You would have to add your credentials to this file path.aws/credentials. Alternatively, you can also use AWS configure and it will set it up for you. There is a lot of information available within AWS's documentation with regards to what exactly you would have to set up. But very briefly, you would have to set up the key ID and the secret access key for the IAM role that you set up that will allow you, or that you will assign permissions to set up the actual SageMaker instance and run it this credentials will be used by MLflow in order to make the entire deployment pipeline straightforward. So you would not have to set up any manual updates once that is complete. So you set this up using the MLflow CLI. You would say MLflow SageMaker build and push container, and that would, once you have this all set up, it would build and push the container to the SageMaker instance. In order to deploy it, you need to know your SageMaker execution role. This is the IAM role that you set up, as well as the AWS region that you are going to deploy the endpoint to. This can be set up within the AWS credentials, but if it is not, you can also specify this within the deployment command within MLflow SageMaker. So you set up your app name, your model URI, best Mario model. This doesn't currently exist, so maybe Ultimate or Wicked Mario model would be a good candidate. The SageMaker ARN itself, so whatever role you set up, as well as the region you would like to deploy it to. If you do not have an AWS account or do not want to deploy to SageMaker, a more generic solution would be to simply create a Docker image. That also is very straightforward. You will set up the CLI with MLflow models build Docker, and then there are two arguments that it takes. The name, this could be again anything as long as it's consistent, and model URI, which is the URI of the actual model itself. Again, best doesn't exist, so you could set it up as Wicked, and versions could be either 1, 2, any version that exists, or a stage, so the production stage as an example. However, do note that if you want to update it, you would have to run the command again, where it would generate and encapsulate the new Docker container with the updated or with the latest version. After this, you could spin up a Docker container with the image. You could use the argument to set it up as a daemon and a port forward 8080 in order to actually run the inference itself. You could then run the inference using the curl command. The image input would have to be a base64 encoded image, but we cannot just send the string, just send a base64 string. We need to include it in a JSON dictionary with the specified format. And once we do that, we could set up bash, which we could run this command within bash, which uses base64 to convert our image into a string. So curl http localhost 8080, which is where our Docker container is running. We set up the invocations endpoint similar to MLflow serve. We define the content type within the headers as a JSON, so it realizes that we are providing it with a JSON input. And finally, we provide it with the data within the post request that contains the base64 encoded Mario_0.jpg file. This could be any image file that you want to get the results for, and it will present to you with the results itself. Finally, there is a couple of typical errors that you will find when setting up your MLflow deployment. So we thought that this would be helpful and is something that you should check out in case you run into any of these issues while you are actually deploying your model. So that is all I have for today. Thank you all very much for sticking around. If there are any additional questions, I would love to take those at this time.
So I want to thank Jinen for a great session. Wait, I'm going to remove the pin so we can see everyone. At this time, we're going to open the stage for questions. So really feel free to open your mic, open your camera if you want. You can also share your questions on the chat, and we'd love to assist in any way possible or take your questions. We have one in the chat, which I'm going to start with. For the this is for you, Jinen. For the use case of a model currently deployed and running from a cloud function in GCP, what process would you recommend for integrating DagsHub?
Oh, this was something that we had discussed as well, I think, in one of the support queries. So it, I guess, depends on the cloud function. If I'm more familiar with AWS, so I'm assuming it's serverless. So if you're using something like that is similar to Lambda, you would ideally set up your project with the MLflow remote. Since you have already set up your trained model and it is deployed in production, you would want to ideally approach it from the integration aspect of things or the lifecycle aspect of things. So the register model Python API function would be useful for that. You would register the model via MLflow. Then within your, or then you would export your actual registered model to the Docker container and then redeploy that updated container with the model URI that you are looking to deploy. Ideally, you would set it up with the staging variable set up. So you would want the models / the actual name of the model / production, and then it will pick up the latest production model that is available for you. And anytime you would want to refresh that update, you would basically have to just restart the serverless function. And when the Docker container initializes the actual model itself, it will set it up with the last updated version of the model. And that should set up a good CI/CD. So if you have a Git repository that you're currently using, you could set up a post hook that would trigger that refresh anytime you update a new model or update the stage for your model.
I think this is a great question, and probably it's a case by case. So if you want, I'm gonna share the link. I'm gonna share a link here to our Discord channel, where we have all of our team there, also for support. And I highly recommend shooting this question with your specific use case in the chat. And we'll be happy to jump on a call and help. So I'm gonna send the link here. So this is the link to our Discord. Another question, a meta question about the talk. Are the recordings for this and previous talks going to be uploaded anywhere on the internet? So yes, we already have all 4 workshops uploaded to in our docs. It's pretty much the same session, but was recorded in a different time. So you can find it on our docs under workshop. So I'm going to send a link here as well. We have a workshop there about like onboarding DagsHub, about DVC and DDA. 2 workshops about MLflow, so experiment tracking and model registry, and another one about Label Studio on how to automate your labeling and annotation process. So you can find all 4 there, with another 2 more about generative AI and transferring files from Google Cloud to from Google Drive to DagsHub, but those are more specific ones. Okay, so I think with that, I want to thank everyone for joining us today. If you have any questions, really feel free to reach out on our Discord. We're there. Also, if you have suggestions, questions, enhancement, anything that we can do, we'd love to hear from you. We really love to engage with the community and engage with the users. So we're open for suggestions about products, toolings, and also events like this, educational events. So really feel free to reach out and we do our best to accommodate that. With that, have a great rest of the day or evening or afternoon. And I wish you all the best. Bye-bye.